Hi, this is Alex from devstories.eu. Astropy, Python for Astronomy, episode 13 of 15. Instead of writing a massive 15-parameter mathematical function by hand to fit a messy spectrum, what if you could just add basic shapes together like Lego bricks and let Python handle the calculus? That is exactly what we are covering today with compound models and custom fits. In Astropy, you rarely need to build complex analytical models from scratch. You take simple, predefined blocks and combine them using standard Python arithmetic operators like addition, subtraction, multiplication, or division. When you add two Astropy models together, you do not get a static array of evaluated numbers. You get a brand new, fully functioning model object. This compound structure knows how to evaluate itself, calculate its derivatives, and track every parameter from the original base models. Consider a specific scenario. You have a spectrum containing two distinct emission lines sitting on top of a flat background continuum. You want to fit this entire structure simultaneously. You start by instantiating a basic polynomial model to act as your flat baseline. Next, you instantiate two separate one-dimensional Gaussian models to represent the two emission lines. To create your final spectral profile, you simply define a new variable equal to the polynomial plus the first Gaussian plus the second Gaussian. Astropy automatically merges them into a single compound evaluation tree. This introduces a common trap regarding parameter access. When you create this compound model, you might wonder how to isolate the amplitude of the second emission line. Since both are Gaussians, they both have a parameter named amplitude. Astropy resolves this collision by automatically appending numeric suffixes based on the order the models were combined. The first Gaussian gets its parameters renamed to amplitude 0, mean 0, and standard deviation 0. The second Gaussian gets amplitude 1, mean 1, and so on. If you ever lose track of what parameter belongs to which component, you can inspect the parameter names attribute of your compound model to see the exact generated list. Now, the second piece of this is fitting data that carries physical units. Astronomical measurements are not just raw floats. Your independent variable might be wavelength in angstroms, and your dependent variable might be flux density in Janskys. Astropy models handle this elegantly through the quantity object. When you pass your data arrays into a fitter, you pass the Astropy quantity objects directly without stripping the units away. The fitter analyzes the units of your input data and the structure of your compound model. It catches dimensional mismatches before the fit even begins. Once the fit converges, the parameters on the resulting model will automatically hold the correct physical units. Your Gaussian means update to angstroms, and your amplitudes update to Janskys. You do not have to write custom conversion logic or strip units before fitting, only to reattach them later. The compound model enforces dimensional consistency throughout the entire process. Here is the key insight. When you use a plus sign between two models, you're not just chaining functions together, you're constructing a single unified equation that maintains strict unit awareness and parameter traceability from the raw data all the way to the final fit. That is your lot for this one. Catch you next time.